In this video, I'm going to go over examples of how to do electron configuration in both long and short form using either an off-bow diagram or the periodic table. Alright, let's start with something easy. We'll try do the electron configuration for argon, which has an atomic number of 18. So we have 18 electrons. So this is called the Aufbau diagram. It's going to help us figure out in what order and in what orbitals we're going to place those electrons. So we have 4 orbitals. In our s orbitals, we can fit 2 electrons, 6 in our p orbital, 10 in our d orbital, and 14 in our f orbital. And we're going to follow these arrows in order to help us know what goes first. So the first one is 1s. So we have 1s, and we can fit up to 2. The next arrow, we have 2s. So we have 2s, and we can fit up to 2. So that's 4 electrons so far. The next arrow, we have a 2p. So I'm going to write 2p, and we can put up to 6 electrons. So now we have 10, 8 more to go. Next is 3s, so 3s, 2. And on the next arrow, we have 3p. So 3p, 6. So that's 2, 4, 10, 12, 18. So there is our electron configuration for argon. Now let's try something else. Let's try calcium, which is 20. Now we can write this whole thing out again, or we can do a short form. So what the short form is we look for our nearest noble gas. So for calcium, the nearest noble gas is argon. So we're going to put argon in square brackets, which is this whole electron configuration. And then we have to place 2 more electrons. So if we continue, we go to 4s, and we can fit 2 electrons. So that's the short form way of doing electron configuration. Now let's try another one. We can do strontium 38. So our nearest noble gas is krypton. And krypton goes all the way up to 4p6. So all I have to do for strontium, which is 2 more than krypton, because krypton is 36, is add our 5s2. Now, how did I know krypton went up to 4p6? Let's look at another way of doing electron configuration where we're going to use the periodic table to help us. So here's our periodic table, and there's a pattern with where all these orbitals are. Here are all your s orbitals, with your s1s being your alkali metals and your s2s being your alkali earth metals, and of course we've got helium over here. This is our D block, so we've got our D1s, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to our D10s. Okay, these are our P blocks, where we've got P1 all the way up to P6, and our F blocks are down here, where we have F1 all the way over to F14. So krypton is right here. This is where krypton is. Notice that it ends in a P block, specifically 4p, and in our 6. So it ends in 4p6. That's why I knew where krypton ended. Now let's use this to try and help us quickly figure out the electron configuration for any element. Let's look right there. Right there is iron. Okay, so the closest noble gas to iron is right here, which is argon. So for iron, we are going to write its electron configuration as argon. And then we have to add. So from this point on, we're going to add a 4s2. So we're going to add 4s2. And then we have these are our 3ds. And we are going to go from 1, 2, 3, 4, 5, 6. So 3d6. And that's all there is to it. Let's try one more. How about gold? Let's do gold. Gold is right here. That's where gold is. So gold's closest noble gas is over here. That would be xenon. So for gold, the electron configuration, in short form, we're going to have the closest noble gas, xenon. And then right over here, we're going to have a 6s2. And then it's important to note right here is where our first f orbital starts. And this is the 4th orbital. So then we're going to have 4f and the whole thing all the way up to 14. Right? And then from here, we continue back to 5d, where we go all the way up to 9. So we have 5d9. All right, let's move on and let me show you some energy level diagrams. So here's an energy level diagram. And for our energy level diagram, I find it a lot clearer to show exactly where an electron is. So let's do an example. Let's do magnesium. So magnesium has an atomic number of 12. So we need 12 electrons. Now in the s orbital, you can fit 2. But we have to look at the Pauli exclusion principle, which says no orbital may contain more than 2 electrons, and those electrons in the same orbital must have opposite spin. So let's give one a spin up and one a spin down. Next we have 2s, so spin up and spin down. And then as we're placing into 2p, we have to remember Hund's rule. Hund's rule says one electron must occupy each of the orbitals in a sublevel before a second electron can be added to any of the orbitals in the same sublevel. So let's, instead of putting a second one in this sublevel, we're going to put one in each. So what do we have here? We have 2, 4, 5, 6, 7 electrons. So now we can add some more where we'll have spin down. So 8, 9, there's 10 electrons. And then we can go up to 3s and place our remaining 2. All right, let's try another one. I'm going to pick an interesting one here. Okay, let's do chromium. So chromium has an atomic number of 24. Now, if we were to write the electron configuration for that using the Aufbau diagram, or if we were to use the periodic table, its closest noble gas is argon. And then we have our 4s2, and it is in our D block, and it is number 4. So then we write 3d4. But let's look at this energy diagram because something interesting happens. So we'll put all those in. So we got our upspin, downspin into 2s, and then 2p, following our rules. Our Hund's rule and Pauli exclusion principle, 3s, 3p, and then we have 4s. And we have this situation here. Now, there are 2 exceptions to the rule here when writing our electron configurations. One is with chromium and one is with copper. So if we look at chromium, we see that the 3d shell isn't quite full. It's not even half full. It's very, very close to being half full. So what it likes to do is it likes to take away 1 from that 4s, and it would much prefer to have that electron here so that that 3d shell is half full. Now in the case of copper, which is 29, copper looks like this initially, where the 3d shell isn't quite full. So it likes to do the same thing. It likes to take this electron and move it over here to fill that 3d shell. And these are our 2 exceptions. So chromium actually looks like this, where we have 4s1 and 3d5. And copper will look like this, where we will have 4s2 S1, and 3d10.